Okay, in this little lecture video, we're going to talk about some of the other roles that hemoglobin plays. So it's not just for oxygen delivery to the tissue, but hemoglobin also functions for H plus and carbon dioxide transport. And this is good because the binding affinity of hemoglobin for oxygen is opposite its affinity for H plus and CO2. So H plus and CO2 are going to be byproducts, waste products of respiration. So it makes sense that hemoglobin brings oxygen to the tissues, releases the oxygen, and then picks up the H plus and the carbon dioxide to get rid of it. So let's take a look at a little bit how that works and how it affects. Since we know it has an opposite effect or opposite affinity than it does for oxygen, let's look at how we can graphically represent that. So let's look at H plus first. So H plus, we know in the muscles, where all this respiration is taking place, we have a lower pH value. So we have the release of protons. And so we also know then, under these conditions, deoxyhemoglobin, which remember is the T state, it has a higher affinity for H plus than it does for O2. So the T state has a low affinity for O2 and a high affinity for H plus. So deoxygenated hemoglobin's job is to pick up that H plus. And this has a name, this opposite affinities. It's called the Bohr effect. So we can take a look on how you can see the Bohr effect in an oxygen saturation curve. So if we were to draw the saturation then of O2, and here's the halfway mark, we know that's important. Here's the pressure of O2 on our x-axis. So here's the regular binding curve for hemoglobin. At lower pH values, this graph is going to shift to the right. Okay, so if we look at that, if we shift to the right, so this is going to be at lower pH, so more H plus, more acidic conditions. So under those conditions, if we shift to the right, then we know, oops, I want to do red, that we have moved the KD from here to here. Okay, so under lower pH, the KD for the binding of oxygen is higher. That means it takes more oxygen to reach the halfway point where half the binding sites are occupied. It takes more oxygen because the affinity is lower. So now let's look also, we have to remember that carbon dioxide is the other byproduct of respiration. So if we look then at how hemoglobin can carry CO2, and we already know one way that CO2 is transported, it's just transported in the bloodstream. So CO2, we know, reacts with water to form carbonic acid, and we know that carbonic acid dissociates to H plus and to hydrogen carbonate. So we know that the hydrogen carbonate just gets carried in the blood. It's part of the blood buffer system. And we just saw with the Bohr effect that the H plus itself just attaches to hemoglobin. So various amino acids get protonated on hemoglobin's surface. And that's how those H pluses get carried up to the lungs. However, we can also do some chemistry with that carbon dioxide. So the carbon dioxide can react with free amino groups hanging off of hemoglobin amino acid side chains. So if you had a free amino group that could react with carbon dioxide, so you get attack, nucleophilic attack at that carbonyl carbon. And that's going to make, oops, I almost tried to erase that with my finger like I was using a real whiteboard. The product of that reaction, then when we've attached that CO2, is carbamate. So you may remember from bingo, we had carbamic acid. Now you know why. And we get a dissociated H plus as well. Okay, so in tissues, we know that this reaction is product favored because we have high CO2 concentrations, which would shift this equilibrium to the right. But in the lungs, where we have low CO2 concentrations, we know that the reactants would be favored. So once hemoglobin carries this carbon dioxide to the lungs, this reaction can go in reverse, release that CO2, and it can be breathed out.